Picture two astronauts. One drifts toward a dark object that bends every photon, swallows every signal, and ends, somewhere inside, in a region the equations refuse to describe. The one who stays behind watches the other approach. He sees her slow, redden, smear across a glowing membrane, and burn. The one who fell never noticed any of that. From inside her own ship, she felt no heat, no edge. She crossed a smooth and empty boundary while still alive. Both reports are correct. The same physics produced them. And the most disturbing part of the puzzle is this: no experiment ever can compare the two stories. The universe seems arranged to forbid the contradiction from being witnessed. That arrangement has a name: black hole complementarity. It was proposed in 1993 by Leonard Susskind, Lárus Thorlacius, and John Uglum to rescue a single principle, that quantum information cannot be destroyed, from a calculation by Stephen Hawking that said it could. The rescue worked. But it forced an even stranger conclusion: that the three-dimensional world of our experience is a hologram of two-dimensional data on a distant surface. That conclusion is now the most cited idea in theoretical physics. By the end of this video, you will understand what the black hole information paradox actually is, how the stretched horizon and complementarity were invented to save it, why the firewall argument shattered the truce in 2012, and what the entire framework points to about reality itself. If you find value in explorations like this, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. To see why black hole complementarity exists, we have to start with a single calculation that broke 1,000 years of physical intuition. The year is 1976. The man is Stephen Hawking, then 34 years old, working at Cambridge. 2 years earlier, he had announced one of the strangest results in modern physics. Black holes are not perfectly black. They glow. They radiate. They give off a faint thermal spectrum of particles, and over enormous spans of time, they evaporate. The radiation is now called Hawking radiation, and the calculation that predicted it combined two theories that physicists had spent half a century trying to reconcile: general relativity and quantum field theory. The paper that followed in 1976 had a quieter title: Breakdown of Predictability in Gravitational Collapse. It appeared in Physical Review D, Volume 14, page 2460, on the 15th of November. In it, Hawking pushed the calculation forward. If a black hole evaporates entirely, if it takes in a star, a planet, an encyclopedia, anything at all, and over an astronomical timescale gives off only thermal radiation in return, then the detailed quantum information about what fell in is not in the radiation. The radiation is thermal. Thermal means information free. Hawking concluded, in his own words, that gravitational collapse represents a fundamental limitation on our ability to predict the future, additional to the limitation imposed by the normal quantum mechanical uncertainty principle. That sentence was the explosion. Translated into the language of quantum mechanics, Hawking was claiming that a pure quantum state, a state with full information, could evolve into a mixed thermal state, a state with information genuinely erased. Quantum mechanics, as physicists had known it for 50 years, was built on a principle called unitarity. Unitarity is the requirement that quantum evolution preserves information. Run any quantum process forward in time, and in principle, you can run it backward. The total probability is conserved. The history is recoverable. Hawking's calculation said that a black hole, if you let it finish evaporating, breaks this. The information goes in, and the information is gone. To make the point vivid, Hawking himself used an everyday image. Burn an encyclopedia. The pages turn to smoke, to ash, to heat radiated into the room. In principle, and physicists insist on the in principle because it is what defines a fundamental law, every word of every page is still encoded in the precise arrangement of those molecules and photons. A sufficiently powerful machine could trace the smoke backward and reconstruct the text. Now drop that same encyclopedia into a black hole and wait. The hole eventually radiates back into nothing, leaving only a thermal glow that, on Hawking's calculation, carries no trace of the words. The information has not been hidden, it has been deleted from the universe. What does it mean that a single calculation, performed by a single man with a notepad in Cambridge, could threaten the foundation of quantum mechanics? Most physicists who first encountered Hawking's argument were not just skeptical, they were rattled. If Hawking was right, then unitarity, the rule that quantum information is conserved, had a built-in exception every time a black hole formed and evaporated. The exception did not require exotic conditions, it required only gravity, time, and patience. Either Hawking's calculation was wrong, or quantum mechanics as practiced was wrong, or some assumption shared by both general relativity and quantum field theory was wrong. The information paradox was born. Before we follow the rescue attempts, we need a second piece, the entropy. 4 years earlier than Hawking's paradox paper, in 1972, a young graduate student named Jacob Bekenstein proposed something that almost no one took seriously at first. Bekenstein was born in Mexico in 1947 to Polish refugees and trained in the United States and Israel. He noticed a curious accounting problem in general relativity. If you throw a hot cup of coffee into a black hole, the coffee's entropy, its disorder, the missing information about exactly how its molecules are arranged, appears to vanish from the universe. The second law of thermodynamics, which says that total entropy never decreases, would seem to be violated. Bekenstein argued that the black hole must inherit the entropy. And after careful work, he proposed that a black hole's entropy is proportional to the area of its event horizon, not the volume, the area. Two-dimensional surface area, measured in Planck areas, the smallest possible patches of space that physics still considers meaningful, squares roughly 10 to the minus 70 meters across. The proposal was strange. Entropy in all other systems we knew scales with volume. Double the size of a box of gas and you double the entropy. Bekenstein was saying that for a black hole, entropy scales with the boundary, not the interior. He generalized the second law. The entropy of ordinary matter plus the area of every black hole in the universe divided by appropriate Planck units, never decreases. Hawking initially objected. His own 1974 and 1975 work on radiation, however, did the opposite of refuting Bekenstein. It confirmed him. The radiation Hawking calculated implied a temperature, and a temperature combined with energy implies entropy, and the entropy turned out to match Bekenstein's area law exactly, with a fixed coefficient of 1/4. The Bekenstein-Hawking entropy formula now reads S equals Boltzmann's constant times the speed of light cubed times the horizon area divided by 4gh bar. In symbols, S equals kb c cubed a over 4gh bar. Each variable carries weight. The area is the horizon surface. The factor of 4 is exact, not approximate, not phenomenological, exact. Keep that 1/4 in mind. We will come back to it. What we have established is this. By the mid-1970s, physics knew that black holes had entropy, that the entropy was proportional to the horizon area, and that a black hole would slowly radiate this entropy back into the universe. The mainstream view was that the radiation could not be carrying out the original information, because Hawking's calculation said it was thermal. The conclusion, if you took it at face value, was that information was destroyed every time a black hole completed its life cycle. For almost 2 decades, the field divided. One camp, led by Hawking, accepted information loss as a feature of the universe. Another camp, led increasingly by a physicist named Leonard Susskind at Stanford, refused. Susskind, born in 1940 in the Bronx, had spent his early career on string theory and confidence that nature would not abandon a principle as deep as unitarity. He took Hawking's argument as a problem to be diffused, not a discovery to be accepted. He later described his stance as a war, a friendly war, fought with respect, but a war over what the universe was actually doing. He titled his memoir of the period The Black Hole War. Stephen Hawking was the opponent. Unitarity, Susskind insisted, was non-negotiable. By 1993, the war had a battlefield. The battlefield was an archive paper posted in June by Susskind, Lárus Thorlacius, and John Uglum. It was titled The Stretched Horizon and Black Hole Complementarity, and it appeared the same year in Physical Review D, Volume 48, page 3743. The paper made a proposal so audacious that, even today, 3 decades later, theoretical physicists have not finished arguing about its implications. It was the proposal of complementarity. The proposal rested on 3 postulates, stated almost as articles of faith. We will state them as the paper does and then unpack them. First, conventional quantum theory applies for the distant external observer. There is a unitary scattering operator. Information is preserved. Second, outside a region called the stretched horizon, located roughly 1 Planck length above the mathematical event horizon, general relativity in its semimassical form remains valid. The big particular relativity in its semimassical form remains valid and substrate many provisons. The main form the paper would be veleb intertraced. The first made informally try to play differently facility and provide problem in the ship. Second, It is the region first pot on the world. There is a unitary scattering operator located roughly 1 Planck length above the mathematical event horizon. Located, it realize them. There is those contimacy is what has made form for Velib general relativity in its small. The problem market, there is also even ever. The different main form about the world recently understanding. The reasonly world was given to overworld and would Elberplack. The main form there is also competition of us, the different main form the paper of stet. There is also important the different empower to the character. The different main form there isn't part, it is the paper of Planck length for the blig tracking empower and several to leaf. The different main form there is also abled every provises. The different main form provote to the left and plaque. The state of operated, surprised and stretched horizon to have born remains valid. Third, black hole entropy, with its 1/4 area coefficient, has a statistical interpretation. It counts microscopic degrees of freedom of the whole exactly as ordinary entropy counts molecular configurations of a gas. 3 innocent-sounding statements. Hold them together, and they produce a result that no one before 1993 had been willing to say. The result is this. To the distant observer, the one watching from a safe distance with telescopes and detectors, a black hole has a hot membrane just above its event horizon. The membrane has temperature. It has electrical resistance. It absorbs everything that falls onto it. It thermalizes that everything across its surface, mixes the bits in with all the other bits already there, and gradually re-radiates them as Hawking radiation. The information is preserved. It is preserved in the radiation. Nothing was destroyed. From this observer's perspective, an astronaut who falls toward the hole approaches the membrane, slows due to gravitational time dilation, gets infinitely redshifted, smears, and ultimately is reduced to thermal noise that escapes back into space over an enormous span of time. To the infalling observer, however, no such membrane exists. The infalling observer, in her own frame of reference, sees nothing remarkable as she crosses the event horizon. The equivalence principle of general relativity, one of the most rigorously tested ideas in all of physics, says that an observer in freefall feels no gravitational field at all. She is weightless. The horizon is invisible to her instruments. She crosses it. She continues. The membrane, the heat, the smear, none of it happens in her local description. She lives for a finite, proper time and is eventually destroyed by tidal forces near the central singularity. But at the horizon itself, on her side of the story, nothing of note occurred. Both descriptions are correct. Each obeys the rules of physics on its own terms. The distant observer's account preserves unitarity. The infalling observer's account preserves the equivalence principle. They are not approximate accounts, they are exact within their domains of validity. And here is the audacity of the proposal. Complementarity insists that no single observer can ever experience both. The infalling astronaut cannot send a signal back to the distant observer reporting what she saw, because the signal would have to travel faster than light to escape the horizon. The distant observer cannot follow the infalling astronaut without becoming an infalling observer herself, at which point her old account no longer applies. The two stories never meet in any frame where they can be compared. The contradiction is hidden by the structure of space-time itself. The name complementarity is borrowed deliberately. It echoes Niels Bohr's principle from the early 20th century, the idea that an electron is sometimes a wave, sometimes a particle, depending on which experiment you run, but never both at once. Bohr argued that this was not a paradox to be resolved, but a structural feature of quantum mechanics. Susskind, Thorlacius, and Uglum were proposing the same kind of structural feature for black holes on a much grander scale. The horizon shows one face to one observer and a different face to the other, and the laws of physics ensure no measurement reveals both faces simultaneously. The stretched horizon itself deserves a closer look. It is not the mathematical event horizon, that abstract surface where escape velocity equals the speed of light. It is a physical membrane conceptually located about 1 Planck length, roughly 1.6 times 10 to the minus 35th of a meter above the mathematical horizon. The Planck length is the scale at which our current theories of space, time, and matter all break down together. A length so small that no instrument has come within 20 orders of magnitude of measuring it. The stretched horizon is the place where, for the distant observer, the rules of ordinary physics still hold, and the rules of quantum gravity have not yet taken over. The membrane has properties: a temperature, an electrical resistance of 377 ohms per square, the so-called impedance of the vacuum, and an entropy density of 1 bit per 4 Planck areas. Yes, exactly that 1/4 coefficient again. The factor of 1/4 Planck areas is the maximum density of information that can be inscribed on any surface in our universe. Hold on to that number. To see what the stretched horizon does, consider an analogy. Think about a swimmer approaching a high waterfall in slow motion. From the riverbank, an observer with a long lens sees the swimmer accelerate, get drawn into the current, smear into a fine spray at the lip of the falls, and dissipate into mist. The spray rises back up. From the swimmer's own perspective, however, she falls through the lip without disturbance, descends into the cataract below, and is destroyed only at the bottom. The bank observer's account is not wrong. The spray is real. The dissipation is real. The swimmer's account is not wrong either. At the lip, nothing locally remarkable happened to her. The two accounts are about the same swimmer, the same waterfall. They simply belong to different observers, in different states of motion, with different access to information. The stretched horizon is the lip. The waterfall is the black hole. And the spray, in the case of the black hole, is Hawking radiation carrying the information back out. What does it mean that the universe might be arranged so that no single observer ever witnesses a contradiction in its laws. That question, the question of what kind of physical universe enforces this protection, is what Susskind and his colleagues did not answer in 1993. They proposed a structure, not an origin. The structure required, they said, certain things to be true about how matter behaves at the horizon. It required that in-falling matter spread out laterally across the entire horizon surface before it crossed. It required that the spreading be governed by what they called the scrambling time, roughly the Schwarzschild radius of the hole multiplied by the logarithm of its entropy. In the case of a solar mass black hole, the scrambling time is somewhere on the order of a millisecond. Information that falls in is smeared across the horizon in a millisecond and then leaks back out over the evaporation lifetime, which, for a solar mass hole, is around 10 to the 67th power years, a number with no useful analogy in any human framework. The numbers are worth pausing on. A black hole with the mass of our Sun, 1.989 times 10 to the 30th kilograms, has a Schwarzschild radius, the radius of its event horizon, of 2.95 kilometers. That is 1.83 miles. Its Hawking temperature is roughly 6 times 10 to the minus 8th Kelvin, or about 60 nanokelvin, 60 billionths of a degree above absolute zero. The cosmic microwave background, the leftover heat of the early universe, is 2.725 Kelvin, about 45 million times hotter than this black hole. What this means in practice is that a stellar mass black hole sitting in our universe today is absorbing more energy from the background than it is emitting. It is growing, not evaporating. Only black holes well below the mass of the Moon, below about 10 to the 11th kilograms, are hot enough to be net radiators today. The complete evaporation of a solar mass hole would take longer than the present universe's age multiplied by something like 10 to the 57th power. The processes Complementarity describes unfold on timescales that make the lifetime of every galaxy a rounding error. These are the bones of the original proposal. We will return to the details, but for the moment, hold the picture in mind. A distant observer sees a hot membrane just above the event horizon, a stretched horizon that thermalizes infalling matter and re-radiates the information. An infalling observer sees nothing of the membrane and crosses a smooth, empty horizon. Both are correct. Both are consistent within their own domains, and no measurement ever in any frame can put the two descriptions side by side. The 1993 paper closed with a question more than an answer. If complementarity is true, the paper asked, then how does it actually work? What is the membrane made of? What microscopic degrees of freedom produce the area law entropy? And, most disturbing of all, does the structure of space-time itself have to be redrawn to accommodate this strange double vision? It would take another 2 years for the answer to begin to take shape. The answer was the holographic principle, and it would change what physicists believe the universe is. The answer came from 2 directions at once. The first direction was an isolated and almost overlooked argument from a Dutch theorist named Gerard Hooft. The second was a paper Susskind himself published in 1995 in the Journal of Mathematical Physics, titled, with characteristic boldness, "The World as a Hologram." Gerard Hooft, born in 1946, had won the Nobel Prize in 1999 for unrelated work on the renormalization of gauge theories. But for years before and after, he had been wrestling alone with what black hole evaporation really meant. He could not accept Hawking's information loss. In a 1993 paper titled Dimensional Reduction in Quantum Gravity, archived as GR-QC 9310026, Hooft worked out the implications of insisting that black hole evaporation, like every other quantum process, be described by a unitary scattering matrix, an S matrix in physicists' shorthand. He demanded that input states map deterministically and reversibly to output states. To make this work, he needed strong interactions near the horizon. Not because the curvature there is large. For a big black hole, the curvature at the horizon can be gentler than the curvature at Earth's surface. The interactions come from a different effect: extreme gravitational blue shift. To an observer far from the hole, a particle plunging through the horizon appears infinitely energetic, because the gravitational time dilation has compressed an entire history into the observer's last moments of view. At those effective energies, every interaction is enormous. An infalling particle, viewed from outside, generates a gravitational shock wave that bends the trajectories of every other infalling particle. The shock waves write information onto the outgoing radiation. The infalling history is imprinted on what comes back out. Hooft then asked, what kind of theory could describe this? And his answer was the genuinely shocking part. He wrote, "At a Planckian scale, our world is not 3+1 dimensional. Rather, the observable degrees of freedom can best be described as if they were Boolean variables defined on a 2-dimensional lattice." The argument was deduced, in Hooft's words, from not much more than unitarity, entropy, and counting arguments. The universe, examined finely enough, has fewer degrees of freedom than its volume would suggest. Its information content fits on a surface, not in a box. Susskind generalized this 2 years later. His 1995 paper extended Hooft's claim from the specific case of black holes to all of physics. The Bekenstein bound, the rule that no region of space can contain more entropy than the area of its boundary divided by 4 Planck areas, is, Susskind argued, a fundamental limit on the description of nature. Any volume can be exhaustively described by data inscribed on its boundary, at no more than 1 bit per 4 Planck areas. He called this principle holography, after the holograms one might see at a science museum. Flat surfaces that, viewed at the right angle and under the right light, project the illusion of full three-dimensional images. Susskind was claiming that what we experience as a three-dimensional world is, in some deep sense, an image of reality coded on a distant two-dimensional surface. This is one of those claims that is easy to repeat and almost impossible to absorb. Take it slowly. The universe you see around you, the table, the room, the stars in the sky, contains, according to the holographic principle, no more information than could be inscribed on its outer boundary. The interior is not autonomous. It is a projection, in mathematical terms, of data living on a surface. The volume is not the seat of the description. The boundary is. What does it mean that the laws of physics permit a complete description of a three-dimensional region using only two-dimensional data? Physicists at the time treated this as a curiosity, an artifact of black hole thermodynamics that might or might not generalize. The skepticism did not last long. In November of 1997, a 30-year-old Argentine theorist working at Harvard, Juan Maldacena, posted a paper to the archive with the title "The Large N Limit of Superconformal Field Theories and Supergravity," archived as HEP TH 9711200. The paper would later be published in Advances in Theoretical and Mathematical Physics, Volume 2, page 231. By 2022, it had been cited more than 20,000 times. It is, by citation count, the most influential paper in theoretical physics since Einstein's general relativity papers a century earlier. The technical content can be summarized in one sentence. Type 2b string theory in a five-dimensional anti-de Sitter space multiplied by a five-dimensional sphere is mathematically identical to a four-dimensional supersymmetric gauge theory living on the boundary of that space. The five-dimensional theory contains gravity. The four-dimensional boundary theory does not. The two theories describe the same physics with two different numbers of dimensions and two different sets of degrees of freedom. And every quantity calculated in one can, in principle, be calculated in the other. This is called ADS/CFT correspondence, where ADS stands for anti-de Sitter space and CFT for conformal field theory. Holography was no longer a vague principle. It was a working duality. There was at least one example, mathematically rigorous, of a higher dimensional gravitational world being identical to a lower dimensional non-gravitational world. The Bekenstein bound was not just satisfied, it was saturated, naturally, in the construction. Edward Witten and the trio of Gubser, Klebanov and Polyakov sharpened the dictionary in 1998. Within a few years, ADS/CFT had become the most powerful tool theoretical physicists had ever possessed for thinking about quantum gravity. Almost all of the work on black hole information that followed was guided, in one way or another, by the lessons of this duality. Through the late 1990s and early 2000s, the consensus among quantum gravity theorists shifted gradually toward the idea that information must be preserved in black hole evaporation. In 2004, at the 17th International Conference on General Relativity and Gravitation, held at the RDS in Dublin on the 21st of July, Stephen Hawking publicly conceded the bet he had made with John Preskill in 1997. He had argued that information was lost. He now agreed it was not. He presented Preskill with a copy of the 8th edition of Total Baseball, the Ultimate Baseball Encyclopedia, explaining with characteristic dry humor that it was a book from which information can be retrieved at will. He added later that he should perhaps have given Preskill the ashes instead. Kip Thorne, the third party to the bet, never conceded. That should have been the end of the story. It was not. In July of 2012, 4 physicists posted a paper to the archive that resurrected the paradox with an even sharper edge. The authors were Ahmed Almheiri, Donald Marolf, Joseph Polchinski, and James Sully, known by initials as AMPS. The paper was titled Black Holes, Complementarity or Firewalls. It appeared in the Journal of High Energy Physics, February 2013 issue, page 62. The argument it made took a few weeks to be fully understood, and when it was, the field went into what John Preskill described on his blog Quantum Frontiers as a state in which nearly everyone seemed confused. The AMPS argument runs as follows. Consider a black hole long after its birth, specifically after the page time, the moment when the black hole has radiated away roughly half of its initial entropy. For the radiation to carry the original information, as unitarity demands, each new Hawking quantum emitted after the page time must be very nearly maximally entangled with the early radiation that has already escaped. Call the new outgoing quantum B and the early radiation E. The B and E entanglement is the channel by which the information leaves the hole. Without it, unitarity fails. But complementarity also requires the infalling observer to see a smooth, empty horizon. For her, the equivalence principle says nothing unusual is happening as she crosses. In quantum field theory, empty at a horizon does not mean nothing is there. It means the modes on either side are themselves entangled, paired up across the horizon in a specific way called the Unruh vacuum. The Hawking quantum B, just outside the horizon, must be maximally entangled with its partner A, just inside. That A and B entanglement is what makes the horizon feel smooth and empty from the infalling perspective. Now we have a quantum entity B that must be maximally entangled with E and maximally entangled with A. And quantum mechanics has a theorem about this. It is called the monogamy of entanglement. A single quantum system cannot be simultaneously maximally entangled with 2 independent systems. The mathematical statement is strong subadditivity of von Neumann entropy. S of A minus B plus S of B minus C is greater than or equal to S of B plus S of A, B, C. Maximal entanglement on both sides violates this inequality. Picture a relay race in which one runner is required to hold both the baton being handed off and the baton already passed. She has only 2 hands. She is required by the rules to be in firm contact with both batons simultaneously, with no slip permitted. Either the rule breaks or she does. Quantum mechanics is the rule. The black hole, Amps argued, has to break. So something has to give. Amps catalogued the choices. Either unitarity fails, but the field had spent 2 decades fighting to keep it. Either effective quantum field theory fails far from the horizon, in a region where it should work flawlessly, or the equivalence principle fails at the horizon. If the A and B entanglement is broken, the absence of that entanglement is observable. A high-energy curtain of radiation appears just at the horizon, an inferno that incinerates anyone falling in. Amps called this the firewall. It was the 3rd option. Pick it, and complementarity collapses, because the infalling observer no longer sees a smooth horizon. Refuse it, and either unitarity or quantum field theory must be sacrificed. The reaction was severe. Polchinski himself wrote on Sean Carroll's blog, "I am now as puzzled about the information paradox as I ever was in the past. And it seems like a good kind of puzzlement that may lead to new insights into quantum gravity." A year later, in Scientific American, he said, "There is a group of people, including me half the time, that thinks there must be some subtle assumption that we've made that's not valid." John Preskill, summarizing the workshop held at the Kavli Institute in late 2012, wrote on Quantum Frontiers that the workshop was invigorating because nearly everyone seemed confused, and noted that there is strong evidence that unitarity is an inviolable principle of physics, and we don't really know how to make sense of quantum mechanics without it. These are not the words of physicists confident in their understanding. These are the words of physicists at the open edge of their field, where the theoretical commitments collide and something is going to have to break. What does it mean when the people best equipped to describe a phenomenon openly say they are confused by it, decade after decade? Hold that question. We will come back to it. The responses to Amps were swift and inventive. The first major response came in January of 2013 from Daniel Harlow and Patrick Hayden, archived as Archive 1301.4504, titled Quantum Computation versus Firewalls. Their argument was a defense of complementarity through quantum complexity theory. They asked, what would it take, operationally, for an observer outside a black hole to verify that the Hawking quantum B and the early radiation E are entangled? To do that, the observer has to collect a large fraction of the early radiation, perform a precise quantum decoding operation on it, distill out the partner of B, and then compare. Harlow and Hayden estimated the computational complexity of that decoding step. Their result, stated in their own carefully hedged language, "We conjecture, but cannot rigorously prove, that the decoding time for Hawking radiation will in general be exponential in the entropy of the remaining black hole. Exponential in the entropy. For a solar mass black hole, that entropy is around 10 to the 77th. Exponential of that is a number whose digits would not fit in the observable universe written at 1 digit per cubic meter. The point is this: the operation that would let the outside observer detect the contradiction with complementarity takes longer than the universe lasts, longer than the black hole lasts, longer, in fact, than any timescale physics knows how to write down. Susskind endorsed the proposal a day later in his own paper, Archive 1301.4505, Black Hole Complementarity and the Harlow-Hayden Conjecture. He concluded, if their conjecture is correct, then black hole complementarity may be alive and well. His diagnosis of the AMPS argument was that it relied on an implicit assumption, the proximity postulate, that the partner modes of a Hawking quantum had to be located near the black hole. Susskind argued that they could instead be located in the faraway radiation, encoded redundantly. The contradiction AMPS had identified existed only if the experiment to detect it could be performed. Harlow and Hayden's conjecture said it could not be. This is the form complementarity now takes in the modern theoretical literature. It is no longer the claim that two observers simply see different things. It is the deeper claim that nature has hidden the contradiction behind computational intractability, that the very experiment to expose it cannot be completed before the black hole evaporates. The information is there. The contradiction is structurally invisible. There is something striking about this resolution. Picture an accountant who suspects a vast fraud at a corporation where two sets of books are kept. One set is given to the auditors. One set is given to internal management. The numbers disagree by enormous sums. The accountant asks, how is this fraud not exposed? The answer, in this analogy, is that the comparison between the two sets of books requires a calculation so long that by the time it could be completed, the corporation itself will have ceased to exist. The fraud is real. The cover-up is structural. No auditor can ever catch it within the lifetime of the institution. Whether you find that comforting depends on how you feel about a universe that, in its deepest physics, appears to be in the business of protecting its consistency from inspection. 6 months after Harlow-Hayden, in June 2013, Maldacena and Susskind together posted a paper that escalated the radicalism of the response. It was titled Cool Horizons for Entangled Black Holes, archived as Archive 1306.0533, published in Fortschritte der Physik, Volume 61, page 781. The central claim is captured by an equation that is also a slogan. ER equals EPR. ER stands for Einstein-Rosen. An Einstein-Rosen bridge is the technical name for a non-traversable wormhole, a thin connection between two regions of space-time that obeys all the rules of general relativity, but cannot be crossed without exceeding the speed of light. EPR stands for Einstein, Podolsky and Rosen, the authors of the 1935 paper that introduced the modern problem of quantum entanglement. ER equals EPR asserts that these two phenomena are the same. Maximally entangled quantum systems, the claim says, are connected by an Einstein-Rosen bridge. Entanglement is geometry. Geometry is entanglement. Read that sentence again. Two electrons in an entangled pair, prepared on Earth and separated by 1 billion light years, are not just correlated. They are joined in some deep sense by a microscopic wormhole. The thread that ties two entangled qubits together is, on this view, literally a thread of space-time itself. This is the resolution Maldacena and Susskind offered to the Firewall Paradox. The AMPS argument assumed that the infalling partner mode A and the early radiation E were independent quantum systems and could not therefore be the same maximally entangled partner of B. Maldacena and Susskind countered, they are connected by a wormhole. The interior mode A is geometrically continuous through a tiny non-traversable bridge with the radiation mode in E. The entanglement is the wormhole. The wormhole is the entanglement. The contradiction AMPS identified is not a contradiction. It is a discovery about what entanglement really is. The proposal was met with the response such proposals deserve: bewildered respect. Susskind reported that Maldacena had sent him a very cryptic message that contained the equation ER equals EPR, and that he, Susskind, had spent days trying to decode it. The paper has since become one of the most influential in the field, but it remains a conjecture. It has no proof. It is supported by suggestive examples, and by its ability to diffuse the firewall. Whether it is literally true, whether you and I are connected by microscopic wormholes whenever we entangle two qubits in a laboratory, remains a question to which the theoretical community gives different answers on different days. The most recent and arguably most precise development came in 2019 and 2020. It is a result about something called the Page curve. The Page curve, named for Don Page, who proposed it in 1993, is the prediction that, if black hole evaporation is unitary, the entropy of the Hawking radiation rises from 0 at the moment of the hole's formation, peaks at the so-called Page time, when the hole has emitted roughly half of its initial entropy, and then falls back to 0 as the hole completes its evaporation. The curve looks like a tent. By contrast, Hawking's original 1976 calculation predicted a monotonically rising entropy that ended at the Bekenstein-Hawking value when the hole was gone, the signature of information loss. For almost 3 decades, no one knew how to derive the Page curve from gravity itself. The SEMTI-L semantic calculation always gave Hawking's answer. The Page curve was what unitarity demanded, but what the equations seemed not to produce. Then, in May 2019, 2 papers appeared on the archive within days of each other. The first was by Jeffrey Pennington at Stanford, archived as Archive 1905.08255. The second was by Ahmed Almheiri, Netta Engelhardt, Donald Marolf, and Henry Maxfield, archived as archive 1905.08762. Both papers used a tool called the quantum extremal surface, originally developed by Engelhardt and Wall, to compute the entropy of Hawking radiation directly from gravitational physics. Both derived the Page curve. The submodule equations, properly understood, did contain the information. They had simply been read wrong for 45 years. The key concept is called the island. After the Page time, the formula for the entropy of the radiation includes a contribution from a region inside the black hole, a region the radiation does not, in any obvious sense, have access to, but which the equations insist must be counted as part of the radiation's description. The formal statement is called the island formula. The entropy of the radiation, R, equals the minimum over all candidate island regions, I, of the area of the boundary of I divided by 4 times Newton's gravitational constant plus the von Neumann entropy of the quantum fields on the region I union R. Speak it. S of R equals the minimum over extremal islands of the area of the island boundary over 4g Newton plus the quantum field entropy of island union radiation. The island sits geometrically in the deep interior of the black hole. It is far behind the horizon, far from the radiation that has escaped. Yet the equations of successfully gravity, when computed carefully, instruct you to assign its information to the radiation. Information that, on every naive reading, is trapped inside the hole, turns out to belong to the outside. In November 2019, a second pair of papers, by Pennington with Stephen Schenker, Douglas Stanford and Zhenbin Yang, archived as archive 1911.11977, and by Almheiri, Thomas Hartmann, Maldacena, Edgar Shagulian and Amir Hossein Tajdini, archived as archive 1911.12333, showed that the island formula arises from new saddle points in the gravitational path integral called replica wormholes. The gravitational path integral, summed over all geometries that contribute, includes geometries in which the interiors of multiple replica copies of spacetime are connected through wormholes. These geometries had been missed in Hawking's original calculation. When you include them, the Page curve appears. The comprehensive review of these results, written by Almheiri, Hartmann, Maldacena, Shagulian and Tajdini, was published in Reviews of Modern Physics, Volume 93, number 35002, archived as archive 2006.06872. The title is The Entropy of Hawking Radiation. For many physicists, this is the strongest evidence yet that information is preserved in black hole evaporation, and that the answer was hiding in plain sight in the gravitational equations themselves for nearly half a century. What does it mean that a calculation performed in 1976, which seemed to prove information loss, was reading the same equations that, performed differently in 2019, prove information conservation? Hold that question too. We are nearly at the end of the presentation. and the time for examination is coming. Throughout this period, alongside the firewall debate and the islands program, alternative proposals continued to circulate. Samir Mathur, working since 2003, has championed the fuzzball proposal, the idea that a black hole has no smooth horizon at all, no interior region, just a horizon-sized ball of strings whose mass is spread throughout, ending in smooth caps. The different fuzzball configurations would be the e⁻⁻⁻ Bekenstein microstates. The firewall, in some readings, is a hot variant of the fuzzball. Gary Horowitz and Maldacena, in a 2003 paper archived as archive HEP DH 0310281, proposed an alternative called the final state boundary condition, in which a special quantum projection at the singularity teleports the information into the outgoing radiation. Susskind himself, with collaborators, has spent recent years exploring the conjecture that quantum complexity equals geometric volume, that the literal interior volume of an ER equals EPR wormhole encodes the computational complexity of the quantum state on its boundary. The slogan has become, "Black holes are the fastest computers in nature." Each of these proposals has its own technical sophistication, its own band of advocates, its own unresolved problems. None has settled the field. Wikipedia, in 2025, still lists the black hole information paradox as an unsolved problem in physics. Recent papers from Raphael Busso and collaborators, including Archive 2507.06046 in 2025, observe that some form of complementarity is still needed to explain the emergence of the interior spacetime of a fully evaporated black hole. After 45 years of work, the paradox endures. It endures with one significant addition. The story has been threaded throughout with observation. The Event Horizon Telescope, an Earth-sized array of radio dishes operated by more than 300 researchers at 80 institutes, released its first direct image of a black hole shadow on the 10th of April 2019. The supermassive black hole at the center of the galaxy M87, 6.5 billion solar masses, 55 million light-years away. On the 12th of May 2022, the same collaboration released an image of Sagittarius A star, the supermassive black hole at the center of our own galaxy, 4 million solar masses, 27,000 light-years away. The ring measured 51.8 micro-arcseconds across, with an uncertainty of 2.3 micro-arcseconds, extraordinarily close to the prediction from general relativity. The project scientist, Jeffrey Bauer, said, "We were stunned by how well the size of the ring agreed with predictions from Einstein's theory of general relativity." Stunned. That is the word he used. Half a century of fight over the interior, and the exterior turns out to agree with Einstein to within a micro-arcsecond. The horizon is photogenic. What lies behind it remains in dispute. Gravitational wave observatories, LIGO, Virgo, and the Japanese Kagra, have also entered the conversation. If the horizon is not empty in the way complementarity asserts, If there is a firewall or a fuzzball or some other reflective structure at or near the horizon, then merging black holes would not produce a clean ring-down signal. There would be echoes, repeated bursts after the main signal, as the gravitational waves bounce between the horizon-scale structure and the photon sphere above it. Vitor Cardoso, Edgar Franzin, and Paolo Pani published the framework in 2016. In 2017, Jahed Abedi, Hannah Daikar, and Niayesh Afshordi published a paper titled Echoes from the Abyss in Physical Review D, Volume 96, page 082004, reporting a tentative signal at the level of 2.5 sigma significance for a combined analysis of 3 early LIGO events. The result was disputed. A reanalysis by Westerweg and collaborators in 2018 concluded that the reduced significance is entirely consistent with noise, and so we conclude that the analysis of Abedi et al. Does not provide any observational evidence for the existence of Planck-scale structure at black hole horizons. The most recent searches, through 2024 and into 2026, report no statistically significant echoes, with upper limits on the time domain echo amplitude near 10 to the minus 24th at 90% confidence. A few post-merger events show low significance excess power. The echo program, as one review puts it, remains an open but promising observational frontier. So we have the picture, a paradox first stated in 1976, a rescue proposed in 1993, called Complementarity, which insists that two observers will see contradictory but self-consistent things at a horizon, and that no measurement can compare their reports. A principle, holography, that emerged as a consequence. That the three-dimensional volume of our universe is described by two-dimensional data on its boundary. A duality, ADS/CFT, that made holography mathematically rigorous in at least one setting. A fresh paradox in 2012, the firewall, that threatened to break complementarity itself. A defense, Harlow Hayden, that hid the contradiction behind computational complexity. A radical conjecture, ER equals EPR, that identified entanglement with geometry. A recent breakthrough, the island formula and replica wormholes, that derives the unitary page curve directly from gravity. And alongside all of this, the steady accumulation of direct observational data from EHT and LIGO that, so far, has shown horizons behaving exactly as Einstein's classical theory predicts, and provided no support for exotic horizon structure. This is the present state of the theoretical universe. Two observers, two realities, one universe that refuses to let them meet. A horizon that hides what is on the other side behind a wall of causal disconnection and computational intractability. A holographic principle that may or may not be literal. An information paradox that is, by any reasonable measure of consensus, still open after half a century. For the past hour, we have presented this material the way the physics community presents it. Now we examine it. Let us return to the foreshadowed assumptions. There are three claims that have been quietly present throughout the presentation, and each requires examination. The first claim is interpretive, that complementarity establishes a universe in which there is no objective reality, only observer-dependent descriptions. The second is metaphysical, that the holographic principle in showing the universe can be described by data on a boundary removes the need for any cause behind the universe at all. The third is methodological, that the long history of theoretical progress, from Hawking's paradox in 1976 to complementarity in 1993 to ADS/CFT in 1997, to the firewall and ER equals EPR and islands in the 2000s, proves that physics will, given enough time, explain everything without recourse to anything outside itself. Each of these claims has been made, sometimes in scholarly papers, more often in popular writing about the subject. Each is offered with the suggestion that the physics demands it. Each, we will see, is a philosophical extrapolation that the physics does not require. Take the first. The claim of observer-dependent reality is sometimes stated softly, as a consequence of complementarity, and sometimes loudly, as in the 2012 paper by Raphael Bousseau and Leonard Susskind, titled The Multiverse Interpretation of Quantum Mechanics, published in Physical Review D, Volume 85, page 045007. That paper proposes that the horizon complementarity of black holes extends naturally to the cosmological horizon of our universe, and links the two-observer structure of black hole complementarity to the many worlds interpretation of quantum mechanics. A more recent paper, archived as Archive 2008.09500, and titled A Black Hole Interpretation of Quantum Mechanics, explicitly frames complementarity as extending Bohr's wave-particle complementarity to include many worlds observers, and draws the analogy between the asymptotic and infalling observers in black holes and Copenhagen versus many worlds interpretations of quantum mechanics. Some commentators, taking these papers as license, draw a much broader conclusion, that there is no fact of the matter about what happens at a horizon. The two observers' descriptions are equally real, and reality itself is therefore observer-dependent. This is the soft form of an old materialist move, the suggestion that consciousness or observation somehow constitutes the world, and that the world cannot be said to exist independently of someone perceiving it. Examine the move carefully. What complementarity actually says is something much narrower. It says that no single observer can make measurements that simultaneously test both descriptions. The distant observer is incapable, by causality, of receiving signals from inside the horizon. The infalling observer cannot send signals back out. There is no shared frame in which the two descriptions can be compared. The descriptions are operationally incommensurable. That is an epistemic claim, a claim about what can be known and measured. The metaphysical claim that there is no objective reality underlying these observations is a separate claim. The two are routinely conflated. They should not be. In the case of ADS/CFT, where the duality is mathematically precise, there is a single quantum state on the boundary that gives rise to the Bok description. That boundary state is unique. It is objective. It does not depend on which observer is looking. The bulk experience of two different observers in the same bulk geometry traces back in the boundary description to the same underlying state. The descriptions are observer relative. The underlying reality is not. To put it sharply, complementarity says we cannot compare two stories. It does not say there is no truth about what happened. The truth, in the only mathematically precise version we have, is the boundary state. It is one thing, not many. The fact that it gives rise to two incommensurable bulk descriptions is a statement about projections, not about ontology. This is exactly the kind of move materialism has often tried to make in other contexts. From the quantum measurement problem, materialism sometimes concludes there is no observer-independent reality. From the relativity of simultaneity, materialism sometimes concludes time itself is unreal. From neural correlates of perception, materialism sometimes concludes the perceived world does not exist. In each case, a limit on what observers can collectively determine is converted, by sleight of hand, into a denial that any objective fact obtains. The logical step is invalid. From "we cannot agree on what happened," it does not follow that nothing happened. From "we cannot simultaneously measure two complementary descriptions," it does not follow that there is no objective state for either description to be of. A locksmith examines a damaged lock. He determines from one angle that the mechanism failed because tumbler 3 jammed. From another angle, a different locksmith concludes the failure originated at tumbler 7. They cannot simultaneously examine the same configuration of internal pins because each examination disturbs the others. From the two-locksmith disagreement, it does not follow that the lock had no actual state at the moment it failed. The lock had a state. The disagreement is about access, not existence. Complementarity is the locksmith's problem at horizon scale. The universe contains the actual state. Two observers can each access part of it in different ways. The physics forbids them from collating their measurements. That forbidding does not erase the state. The state is what ADS/CFT calls the boundary CFT. It is what 't Hooft's S-matrix is meant to compute. It is, by the consistent insistence of theoretical physicists who built complementarity in the first place, objective. This is the rational position. The materialist extrapolation, that complementarity proves there is no objective reality, is a philosophical leap unsupported by the physics. It is the leap atheist commentators sometimes need to make in order to construct a universe without an anchor. The physics does not provide the anchor's absence. The physics provides only a limit on simultaneous measurement. What does it mean that the most precise theoretical framework we have for black holes contains at its heart a unique objective state, and that the only way to read it as no reality requires importing assumptions from outside the physics? The physics is consistent with classical theism. It is the importations that are not. Move to the second claim. The claim is that the holographic principle, in describing the universe as data on a boundary, removes the need for any cause of the universe at all. The argument runs roughly: if the three-dimensional bulk is dual to two-dimensional boundary data, then the bulk is just a projection. Projections do not require external explanation. The universe is self-encoded. It needs no origin. The argument has rhetorical force. It does not survive examination. Consider what holography actually does. It establishes a mathematical duality. Two descriptions, one in higher dimensions and one in lower, are equivalent. Every quantity that can be calculated in one can be calculated in the other. This is a powerful structural result. It tells us something about the nature of the relationship between gravity and quantum field theory. It tells us nothing about origins. The duality maps one description onto another. Both descriptions exist. Both contain finely structured laws. Both contain energies, fields, configurations. The question of why there is a boundary CFT to begin with, why those specific degrees of freedom exist in those specific numbers with those specific interactions, is utterly untouched by the duality. The holographic principle is a translation rule, not an origin story. Consider the analogy of an architect's blueprint. Suppose you are shown a blueprint of a vast and intricate building. The blueprint, on a flat sheet of paper, completely specifies every wall, beam, conduit, and outlet of the three-dimensional structure. You can, in principle, reconstruct the building from the blueprint, and the blueprint from the building. The two are dual. The blueprint is the boundary description, the building is the bulk. Has the duality answered where the building came from? Has it removed the need for an architect? Of course not. It has simply pointed out that the building's design can be encoded on a smaller medium. The architect's intention is required for either. Whether you point at the building and ask, "Why does this exist?" or at the blueprint and ask, "Why does this exist?" the question is the same. The duality moves the question. It does not answer it. The holographic principle does the same thing. It tells us that the bulk three-dimensional content of a region is fully encoded by the boundary two-dimensional content. It does not tell us why the encoded data has the values it has, why the laws of physics they describe permit life and consciousness, or why anything exists to encode at all. To claim otherwise is to mistake a translation for an origin. This is a recurring move in attempts to escape the cosmological argument. The cosmological argument observes that the universe began to exist, a conclusion supported by the standard model of cosmology, and that what begins to exist requires a cause. The materialist response sometimes points to mathematical equivalences, holography, sometimes to physical mechanisms, the Big Bang itself, inflation, sometimes to speculative ensembles, the multiverse, and claims that the cause has been identified or dispensed with. In each case, the move is identical. A description is offered of how the universe is structured, or how it began to expand, or how it might be one among many. The question of why there is structure at all, why there is anything to be described, is not answered. It is bypassed. There is a name for an argument that bypasses the question it pretends to answer. It is called an evasion. Recall the apologetic argument from infinite regress. The argument runs as follows. Everything in our experience is dependent on something else for its existence. A chair is supported by the floor by the building's structure, the structure by the foundation by the earth by gravity, gravity by the mass-energy distribution, the mass-energy distribution by initial conditions at the Big Bang, the initial conditions by what? At some point, the chain has to terminate. If the chain extended infinitely backward, in the sense that every link was dependent on a prior link with no first link, nothing would ever come into being. We exist. Therefore, the chain terminates. It terminates in something that is not itself dependent on a prior cause, something uncaused, eternal, and self-existent. The materialist option is to declare that this terminus is the universe itself, or the underlying quantum vacuum, or the mathematical structure of the laws of physics. The theist option is to declare that the terminus is a cause that possesses the attributes the universe lacks, namely intelligence, power, and the capacity to give rise to the finely structured order we observe. The holographic principle shifts the location of the terminus without removing it. Instead of asking why there is a three-dimensional universe, you can ask why there is a two-dimensional boundary CFT. Either you have to terminate the chain somewhere, or you have to admit it never terminates, which means nothing exists. The question of what to terminate it in is the same question dressed in different dimensions. The third claim is the methodological one. It says, physics has made progress. From the original paradox in 1976 to the firewall in 2012 to the islands and replica wormholes in 2019, the field has steadily advanced. Given another 50 years, surely it will finish the job. The information paradox will be solved. The universe will be fully described in quantum gravity. There will be no remaining gap for any non-physical explanation to occupy. This is the most common form of the materialist promissory note. It is usually called science of the gaps. It says, we do not know the answer yet, but we will. Trust the trajectory. Examine the trajectory carefully. The information paradox has been open for 45 years. In that time, the field has produced complementarity, the holographic principle, ADS/CFT, AMPS, ER equals EPR, Harlow-Hayden, fuzzballs, final state proposals, islands, and replica wormholes. Each of these is a substantial theoretical achievement. Some, especially ADS/CFT and the recent island formula derivation of the Page curve, are extraordinary. The field has not been idle. And yet, Wikipedia in 2025 lists the black hole information paradox under unsolved problems in physics. Joseph Polchinski, writing in 2012, said he was as puzzled as I ever was in the past. John Preskill, in late 2012, wrote that nearly everyone seemed confused. Recent papers from 2025 including Archive 2507.06046 by Busso and collaborators, observe that some form of complementarity is still needed to explain the emergence of the interior spacetime of a fully evaporated black hole. After 45 years and the labor of dozens of the world's most brilliant theoretical minds, the basic question of what an infalling observer actually experiences and what happens to the information he or she carries is unresolved. What does it mean that a problem central to the foundations of physics has resisted resolution for nearly half a century, through cycle after cycle of brilliant proposal and counter-proposal, and that the people closest to the problem describe themselves as puzzled, confused, and rattled? Consider what happens when a computer's operating system has a flaw that no patch can fix. Every application runs normally, every file opens, every calculation completes. The flaw is invisible, as long as no process demands something the operating system was not built to handle. Then, one program makes an unusual request, and the system crashes. The crash does not look like an operating system failure. It looks like a problem with that one program. So the developers rewrite the program. They patch the call. They add a workaround. The crash returns under a different program in a different way. Patch after patch, workaround after workaround. The crash never goes away. At some point, the developers stop blaming individual programs. They start asking whether the operating system itself is misconceived. The information paradox is the persistent crash. The patches are complementarity, the firewall, ER equals EPR, the islands. Each patch resolves one specific contradiction by introducing another set of unverified conjectures. Complementarity introduces the stretched horizon. The firewall introduces a high-energy curtain. ER equals EPR introduces a wormhole connecting every entangled pair in the universe. The island formula derives the page curve in lower-dimensional toy models that have not been extended to four-dimensional, asymptotically flat spacetime. The unresolved status is not a temporary state on the way to a final answer. It is what the field looks like when its underlying assumptions that quantum gravity can be derived from quantum field theory and general relativity without supplementation have been pushed to their limit. The science will explain it rebuttal requires that the trajectory of physics convince us a complete explanation is within reach. The actual trajectory, half a century of partial wins shadowed by unresolved foundational problems and openly admitted confusion, does not provide that confidence. It provides the opposite. It provides a glimpse of how hard a comprehensive natural explanation is, and how willing the practitioners themselves are to admit on the record that they do not have one. This is not a denial of the work. The island formula derivation of the page curve is one of the most beautiful results in modern theoretical physics. The Event Horizon Telescope's images of M87 and Sagittarius A* are triumphs of observational ingenuity. The 7-decade pursuit of black hole information has yielded genuine, profound, durable knowledge about the structure of the universe. What it has not yielded is closure. And the absence of closure after such an extraordinary expenditure of intellectual effort, is itself a datum. It tells us something about the limits of the materialist program when applied to questions of fundamental ontology. Now consider the fourth thread, which has been quietly present throughout, the question of fine structure. The Bekenstein-Hawking entropy formula has an exact coefficient. It is 1/4. Not approximately 1/4, not phenomenologically close to 1/4, exactly 1/4. The maximum information density on any surface in our universe is exactly 1 bit per 4 Planck areas. The Bekenstein bound, the holographic principle, the entire scaffolding of horizon thermodynamics depends on this coefficient holding to arbitrary precision. Why 1/4? Physics describes that it is 1/4. Physics does not describe why. Susskind's holographic principle assumes it. A DS/CFT confirms it. No proposal explains it. Picture a combination lock with a single dial. The dial runs from 0 to infinity. It is fixed at the value 1/4, and the entire architecture of black hole thermodynamics depends on its being there. Move the dial by any amount and the framework collapses. Entropy stops scaling with area. The Bekenstein bound fails. Holography ceases to be exact. The dial is at 1/4. It has always been at 1/4. It will always be at 1/4, and there is no theoretical principle in any current proposal that requires it to be at this specific value rather than another. Now picture not one such dial, but the family of constants that govern the universe. There are at least 26 independent constants of physics that the Standard Model and general relativity require. Each is fixed at a value that, if it were even slightly different, would result in a universe in which atoms could not form, or stars could not ignite, or chemistry could not yield complex molecules, or galaxies could not assemble. The gravitational constant, the strength of electromagnetism, the strength of the strong nuclear force, the strength of the weak nuclear force, the mass of the electron, the mass of each quark, the cosmological constant, every one of them sits on a knife's edge. The cosmological constant is the most extreme. Theoretical estimates of its natural value place it at something like 10 to the 120 larger than the observed value. The observed value is fine-tuned against the expected natural value to 1 part in 10 to the 120. There is no physical principle that explains why this is so. There is only the observation that it is so, and that any other value would produce a universe in which we could not exist. Now add the 1/4. Add the impedance of the vacuum, 377 ohms per square. Add the dimensionless ratios of fundamental forces. Add the masses, the couplings, the mixing angles, the symmetry breaking patterns. Each one of these is a dial, set to a specific value that the laws of physics require to be set there for the universe as we know it to exist. What does it mean that 26 independent dials all point in the same direction? What is the name for a coincidence of this magnitude? This is the part that stays with me. Not the scale, the precision. Precision requires decision. The materialist response to the fine-tuning problem is the multiverse, the proposal that infinite universes exist with random combinations of constants, and we simply happen to be in one where they permit life. The multiverse has no observational evidence. It is unfalsifiable in principle. No observation could distinguish a universe in which only one universe exists from a universe in which infinite universes exist. The multiverse is invoked specifically to evade the conclusion the evidence suggests. It is, in the truest sense, naturalism of the gaps. The mainstream response sometimes is honest. Martin Rees, the former Astronomer Royal, has written that the constants of the universe appear tailor-made for life. The word tailor is decisive. A tailor is an intelligent being who deliberately fits material to a purpose. The metaphor presupposes the very thing it is intended to evade. The universe looks like the product of a decision. The multiverse is invoked to explain why it does not have to be the product of a decision. The invocation is unfalsifiable, unmotivated by data, and admitted by its proponents to be philosophical rather than physical. Now bring the threads together. The information paradox is 45 years old and unsolved. Complementarity, the principle invoked to diffuse it, is the assertion that the universe is structured to protect its own consistency from inspection. The holographic principle, the principle invoked to make complementarity work, says that all the information in a region can be encoded on its boundary at a finely tuned density of 1 bit per 4 Planck areas. The cosmological constant is fine-tuned to 1 part in 10 to the 120. 26 independent fundamental constants are all set within narrow, life-permitting windows. The horizons of observed black holes match Einstein's century-old equations to within micro-arcseconds. The materialist asks us to believe that the persistent, unresolved character of the information paradox is a temporary inconvenience, that the boundary, CFT, in ADS/CFT, is just a mathematical convenience, requiring no further explanation, that the 1/4 coefficient is a brute fact, that the 26 fine-tuned constants are an accident or a multiverse selection effect, and that the underlying universe, whose laws are so consistent and so finely structured that no observer can ever, by design, witness a contradiction, is the product of nothing but the laws themselves. This is not a conclusion drawn from the evidence. It is a worldview imposed on the evidence. The evidence, examined honestly, points elsewhere. Picture a building inspector who arrives at a vast and unfamiliar structure. The walls are perfectly aligned. The wiring is laid with extraordinary care. The mechanical systems are coordinated in ways that suggest a single intelligence behind them. Every measurement the inspector takes confirms the integrity of the design. He turns to the developer and says, "Where are the blueprints?" The developer answers, "There never were any. The walls just happened to align. The wiring just happened to thread itself." The building is the result of chance arrangements of materials over a very long time. The inspector is patient. He asks, "How long?" The developer says, "Sufficiently long. Trust the process." The inspector replies that no amount of time can substitute for design. The developer accuses him of intelligent builder of the gaps. That is the present state of the materialist account of the cosmos. The dialogue is not a caricature. It is, in slightly more elaborate language, the actual response naturalism offers when confronted with the cosmological constant, the Bekenstein bound, and the systematic protection of physical law from contradiction. The walls are too well aligned to be accidental. The naturalist insists there was no architect and pleads, in lieu of evidence, for more time. There is a passage from John Preskill's Quantum Frontiers piece that bears reading again. He wrote that there is strong evidence that unitarity is an inviolable principle of physics, and we don't really know how to make sense of quantum mechanics without it. Inviolable. The word is theological in its weight. Preskill is using it to describe a principle of nature that, on the evidence of physics, cannot be broken. The history of complementarity, in one reading, is the history of the lengths physicists will go to in order to preserve such an inviolable principle. They will postulate stretched horizons. They will propose firewalls. They will identify entanglement with geometry. They will construct islands inside black holes. They will spend half a century on a single problem rather than concede that unitarity might fail. What does it mean that physicists, while professedly committed to the absence of any cause beyond the physical, treat certain principles of physics as if they were sacred? It means, perhaps, that the structure of the universe has the kind of inviolability that the universe, as an effect, ought not to possess on its own, and that what the physicists are responding to, in their willingness to defend unitarity at any cost, is the imprint of something behind the laws that does possess such inviolability. That something, in the rational analysis of the evidence, is what classical theism has long named the necessary, eternal, intelligent
cause. It is what the cosmological argument terminates in. It is what the fine-tuning argument points to. It is what the design argument requires. It is what the existence of a finely structured, internally consistent, and observation-resistant universe, finely tuned to 1 part in 10 to the 120 in its cosmological constant alone, gives us every rational reason to expect. What materialism gives us, in answer to the same evidence, is the claim that we should not have expected anything, that the constants could have been any value, but they happen to be this value, that the boundary CFT could have any structure, but it happens to be this one, that the laws could have permitted contradiction, but they happen to protect against it. The materialist answer is, at every step, that the evidence is a coincidence. A coincidence of 1 or 2 facts is plausible. A coincidence of 26 independent facts, every one of them pointed at life and consistency, is not a coincidence. It is the signature of intention. This is the rational conclusion. The evidence has been examined, the materialist proposals have been weighed against the data, the naturalistic patches, multiverse, brute fact, future progress, have been measured against what they would have to explain. The data points in one direction. The universe has the structure of a created thing. It exhibits design. It exhibits fine structure. It exhibits the kind of internal consistency that does not arise from unguided matter. And the practitioners of its most advanced physics openly admit, in their own words, that they cannot make sense of its foundations without principles they treat, in practice, as inviolable. Inviolable principles. Designed precision. Causal protection of consistency at the very edges of space-time. The rational reading of the evidence points to an intelligent cause. It points to a cause that exists outside the physical universe it produced, that possesses the knowledge to specify 26 fine-tuned constants, that possesses the power to give rise to the holographic structure of reality, and that possesses the will to do so. This is the conclusion the evidence supports. The materialist alternative is not a conclusion. It is a refusal to draw one. Let me bring this exploration to a close. We began with two astronauts. We end with what their disagreement teaches us. The distant observer sees a hot, stretched horizon, thermalizing and re-radiating everything that falls in. The infalling observer crosses a smooth, empty boundary as if nothing were there. Both descriptions are correct. Neither can be revised without breaking principles physicists hold inviolable. The structure of space-time hides the contradiction from any observer who might compare them. Around this disagreement, half a century of theoretical physics has built an extraordinary architecture. The Bekenstein-Hawking entropy law, fixed to a coefficient of exactly 1/4, the holographic principle, declaring that all the information in any volume of space fits on its boundary at 1 bit per 4 Planck areas. ADS/CFT, the most cited result in theoretical physics. The firewall, ER equals EPR. The island formula, the replica wormhole. Each one a magnificent piece of work. Each one a partial answer that leaves the underlying paradox unresolved. Each one, according to the field's own most distinguished practitioners, falling short of explaining what happens at the horizon to an observer who is genuinely there. What the evidence shows, when examined honestly, is not a universe that the materialist account can close. It is a universe finely tuned to 26 independent constants, including a cosmological constant fine-tuned to 1 part in 10 to the 120. It is a universe whose laws are arranged to forbid any observer from ever witnessing a contradiction. It is a universe whose most fundamental description, on the holographic reading, requires data inscribed on a boundary at the absolute maximum density physics permits, and offers no account of why that boundary exists at all. This is the evidence. The rational conclusion is that the universe is the product of an intelligent cause, a cause that exists outside space-time, that possesses the knowledge to specify constants to 1 part in 10 to the 120, and that possesses the will to set them in life-permitting configurations. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds.
We touched briefly here on what it means for two observers to hold opposite truths about the same event. But a paradox in non-gravitational quantum mechanics asks the same question in an even sharper form, and I have followed that thread much further in an earlier exploration. If the question of how observers can experience genuinely different realities stayed with you, you'll find where on the end screen now and in the description below. Two observers, two realities, one universe that refuses to choose, and behind it, the imprint of a cause that does. Good night.